Okay. Hello, everyone. Let's see, some more people are joining us.
Good afternoon.
Hi. How was your weekend? I hope you enjoyed it. Okay. We have around 25 people, so I guess not so many will join us more, but still some people are coming. Okay, guys, so do you have any questions with regards this our last topic we discussed was we started with laws of motion, and we discussed two first laws of motion. So I guess everything was clear, but maybe I will just refresh you a bit what we did last time, what we were discussing last time, because today we will also consider the third law of motion, which is quite straightforward. And then we will move forward to do some, to consider some cases of possible applications of this law of motion. So you have more experience in considering these options. And I believe it will be definitely helpful for you when you try to understand how to solve some problems. Okay. Let me change. Yeah, if you have any questions along this discussion, you're welcome to interrupt me and ask.
Excuse me, Professor.
Yes, do you have a question?
Before we start, can I ask about the grading of the long kappa assignments?
Sure. Yeah. What?
How they would be graded? Like, what is the benchmark of the
Each problem will
have the points, I guess, of the problems.
Yeah, as I understand, each problem will have certain weight and depends on its complexity, but most of them are kind of similar. So it's kind of very straightforward. It's either fits in this range of answers, which is accepted for the problem and considered to be like graded as some certain points which you get, or it doesn't fit in this range. And also be very careful with the punctuation, like the format and units. I understand some of you have complaints. I received several emails that you answered like correct. It's like correct answer, but with comma instead of dot, and long kappa considers it as a wrong answer. So I understand your point of view. It's reasonable to claim that this is a correct answer, but just keep in mind our conditions nowadays. We cannot check it, like we don't have contacts during the lectures and solving also recitations classes. And we like, it's actually not neither mine nor yours decision. The administration of the school decided that all this work will be done via Long Kappa, and Long Kappa just designed in this way. So we have no many options to change these features, and we need to follow the rules which are accepted in Long Kappa. And that's why there is a detailed information on punctuation and all other features of Long Kappa in the manual. Please carefully read that and be very serious about this, because again, we have not only homework assignments, but also midterms and exams. And all of them will be carried out on the platform of Long Kappa. So these aspects are very important along all course, and eventually it will have an impact on your grade. So we will have still some meetings with all professors involved in delivering this course, and discuss some options. Maybe, I don't promise you anything, but could be that there is an option to consider the lowest grade for 1 week assignment and eliminate it from the total grade. So something similar to midterms. We know that we have 3 midterms, and the lowest grade for midterm, one of the the lowest grade of 3 midterms will be eliminated from the final grading. But we'll see what decision will be made, because in any way it has to be agreed by the head of department and also the dean. So we are still in the process of discussing this, but in any way you are interested to get as many points on each assignment as possible. That's why it doesn't change much your motivation to do this work well. And I encourage you to be very careful with the answers. Nowadays, it's not only important to solve correctly the problem, but also to submit it in the right format, because we deal with this software.
Okay, Professor, and what was the range on the week 3 assignment? Range of the points?
Oh, I mean, I'm not sure exactly. We will.
Okay, I will ask Professor Azamat about it, I guess. Thank you.
Yeah, you could ask him. I'm not sure exactly number of points, but I will be involved in copying and saving all these grades in the near future. So maybe I will be able to answer this question more accurately.
Okay, thank you.
Mm-hmm. Okay. Good. So we have 47 people. Right? Good. So let us then switch this camera and just shortly refresh what we have done.
Excuse me. Hello?
Oh, excuse me?
Before you begin, can I ask one quick question?
Sure.
In Lon Kappa, what value of G we have to take when we calculate our problems? Because there was a number of problems where the actual answer was different from mine because of the difference in
I
hundreds
think this
or
is 9.81.
9.81. Okay.
Yeah, I guess there's the issue, what you're talking about, with number of essential, like amount of essential numbers.
Are you sure about that? Because I was taking this value constantly, and 3 of my problems are shown as incorrect.
Okay, today, as I mentioned, not today, this week, I'm not sure, it will be maybe Wednesday or Thursday, we will have this meeting and let's address this question.
Okay, sorry for interrupting.
Yeah, no problems. It kind of relevant information, but it also, I believe that it should be also in the context of the problem. If other numbers are given with two essential, like 3 essential numbers, like 2 numbers after decimal point, it should be 981. If it's just one number, usually it's 9.8. But yeah, this long kappa requires to be very accurate with this. I will definitely raise this question during the meeting, and hopefully by the end of the week, we'll have more information on this. Okay, thank you. Good, so let's start from the first law of motion, and we claim that again, in the case of inertial frame of references, which definition we gave in details for during last discussion. So in the case of inertial frame of reference, when the sum of all forces as vectors applied to the body is equal to 0, so some resultant force is equal to 0, it either continues its straight and uniform motion with constant excuse me, do you ask him some question? Oh, okay, guys. If you are not asking any questions, please mute yourself so we don't interrupt each other. Okay, so the velocity vector is going to be constant, and this is important that it's going to be constant by absolute value and by direction. So we don't have any change in the velocity vector, so it will continue its uniform motion.
Ернур Булатов, выключи микрофон.
Yeah, please, guys, those who don't ask questions, please mute yourself. Yeah, thank you. Okay, and if our body doesn't move, so it will not move anywhere, and its velocity vector will be equal 0. So, sorry, it's like twice 0, which is not good. So either it stays constant, or it will be equal to 0. So there is no acceleration. That is the main point, and that is the definition of the first law of motion. If the net resultant force is equal to 0, no acceleration. Second law of motion is force is equal to inertial mass multiply acceleration. So I highlighted this moment during last discussion session, that there is a difference between like conceptual difference between inertial mass, which goes into this equation for the second law of motion, and gravitational mass, because physically they describe different features of matter. So first one, it shows how difficult to accelerate the body, how much it resists to be accelerated by some force applied to it. And gravitational mass describes how much it interacts with the gravitational field. So they have different physical background, but it happens that they are equal to each other. So we in details described last time how we can measure acceleration, how we can measure this inertial mass using a spring, and then of course we can determine the applied force. So now it's time for the third law of motion, and this is following. So it can be given in the following form. Minus F to 1. So what does it mean? So if we have two bodies and one body acts on another body with certain force, which is F12, so the second body will react with the same force in absolute value, but in opposite direction, which is force F21. So when we have exert any force on a body, it always will react with the same force, but in a different direction, like opposite direction from the force we apply to this body. And these are three laws of motion which can describe and explain why, so answer also the question why bodies move this way or another. So if, for instance, we have some body on a plate in gravitational field next to the Earth, so we have some weight of this body, and since it stays in stationary condition, it doesn't move downwards, this force is compensated by N. So these are vectors. N, capital N, stands for normal reaction of the surface on which this body is located. So normal means like it always directed 90 degrees perpendicular to the surface. And as a result, we can write the second law of motion for this case will be ma equal to m. Let's say we have axis x going downwards, then mg is positive, then minus n, and this will be equal to 0. So we don't have any, so from here we can claim that acceleration is equal to 0. So we don't have any acceleration because two forces are compensated. Okay, so let's consider more interesting case, in particular some tilted inclined plane. So it will be some angle theta. Assume that we have some body here. This is mg, weight of this body. Then in order to get this case in like convenient for our consideration, it would be good to have our system of coordinates arranged in this way. So it will be X and this will be Y. So keep in mind that we have we need to consider the projection of this weight of the body on our axis. And one projection will be along the y-axis, another along the x. So this can be done like this. And here is our projection on x. Maybe this one a bit longer. Well, something like this. So since this angle is theta, and this is angle of our plane with respect to the horizontal plane, to horizon, then the angle between normal to this plane, which will be along y-axis, and the vertical will be also equal to theta, because here we have a vertical line and angle to the normal of the plane, and here we have the plane and the horizon. So it just shifted by 90 degrees, but the angle between these two directions stays the same. So then we can write that here we have another vector, which is our reaction of the surface. It's always, as I mentioned before, it's always like normal to the surface. And we have, in this case, some net force, which is directed along axis x and pulls this body downhill. So let us figure out what is what. We know that along axis y, these two forces are compensated each other, N and projection of mg. So we have here mg cosinus theta, this force which goes perpendicular to the surface of the plane. And we can write that for y-axis, we have better to start with n because n is positive. We have n, this is reaction of our surface, minus mg cosinus theta equal to 0. So they compensate each other. In direction of y, this body will not move. However, there is another direction x, and here we have some, keep in mind that in this particular case, we do not consider any friction. So we will come back to friction, like not come back, we will come to friction just in few moments. We will discuss different types of friction forces. But now we consider a case without any friction. So there is no force which prevents motion of this block, of this body along the surface of our plate. Then we have mg. Well, so since we have already projections here, we should not consider vectors. Mg sinus theta. So we are talking about this part. Sinus theta equal to, it's positive because it's directed along the axis x, equal to ma. We get some certain acceleration. And this is nice because by changing this, by considering some very long plane and very small theta, the small angle with respect to horizon, we can kind of reduce the acceleration which body will get because of gravitational force. So this is a good experimental platform to calculate the acceleration of free fall, because if you just throw the body in and it moves vertically from top to down, it happens very fast and it's difficult to do correct measurements with high accuracy. But if you put such, for instance, it could be close to this case, could be some metal ball on the inclined surface, where so it can rotate, and friction of rotation is very small, so you can at some extent neglect with this friction. So from this equation, you can see that m and m we can cancel out, and g is equal to a divided by sinus theta. So we can measure acceleration with which this body will move downhills. It will be way like smaller than acceleration of free fall, will be higher accuracy, and then calculate the acceleration of free fall. So this is one of the case when we need to consider the weight of the body projected on different axes, y and x. We will come back to this when we consider friction. So, and see what will be some acceleration, net acceleration, while we also have additional force, which is friction. Okay, another example. Let's go to next slide. Another example is kind of well-known case of an elevator. If there is some body in elevator, when elevator doesn't move and acceleration is equal to 0, so we have weight of the body, which is mg, and also reaction of the surface, n, and they compensate each other. However, so we can write that ma is equal to mg minus n, and this is equal to 0. So acceleration is equal to 0. However, when this elevator starts to move, we get some acceleration. For instance, we go upwards. So we get another equation, minus ma is equal to oops, better. Then we can write that mj plus ma minus n is equal to 0. So our reaction of the surface will be n equal to mj plus a. So when it moves with some acceleration a upwards, our reaction to the of the surface, total weight of the body will be increased because we have additional acceleration of this mobile, in this case, not inertial frame of reference. So that this force has to be taken into account. If it moves downwards,
Sorry, isn't it mg minus ma minus n is equal to 0?
So the thing
The
is,
second thing.
yeah, so it's the thing is that the force is directed to like opposite, it has opposite direction to acceleration. So that's why this ma as a force will be directed in the same way as a weight, and then we sum it up.
Okay.
So if we have our acceleration which goes downwards, this reaction of the surface will be mj minus a, and we will have kind of reduction of the weight of the body, even up to this point when j is equal to a. So we can get something like condition of free falling. So we continue to fall down in gravitational field, but this elevator will move in the same with the same acceleration. So this surface, which should give certain reaction n, will just go in this with the same acceleration, and that's why there will be no force applied to the surface and no reaction of the surface. So in this case, n will be equal to 0. So it will be like free falling condition. But of course, definitely not good to experience something like that in elevator. That's why they have special safety features which block the motion of elevator when it starts to fall. And usually this doesn't happen anymore, but in the early times of elevators, it was actually a big problem, and many people were wounded and died because of these issues when elevators were falling down. Okay, so now let us go to the friction forces. This is important part of dynamics. We know that, let's consider somebody on a surface. This surface is not good. Let's try again. More straight. Okay, we have somebody on the surface. As we mentioned before, we have mg. Then we have reaction of the surface. And if we apply some, imagine, I don't know, some box, we apply certain force, F, and it doesn't move. So looks like violation of the second law of motion, because we know that there is force is equal to ma, so definitely it has some given mass, and you apply a certain force, so it should result in some acceleration. However, it doesn't happen, and we know this just from everyday life. You need to apply some minimum force to push start moving the body. And this is so-called static friction force. And this, let's call it like this, like static, equal to mu static multiply n reaction of the surface. So this is static friction force, and mu is the coefficient of static friction, which is defined by the conditions of two surfaces of our body and the surface on which it's rested. And it will depend on roughness of these surfaces and different other conditions. So that's kind of some experimental parameter which you need to determine specifically for two given surfaces. And then n is the reaction of the surface. And here we don't have surface, so the area does not matter in this case. The static force is defined only by these two parameters. So the heavier object, the larger static friction force will be. So once we get this condition when applied force is equal or larger to static friction force, this body will start moving. And let's say with which acceleration this body will start moving if applied force is equal to static friction force. So in this case, they will just compensate each other. Yeah, and
Mu n divided by m.
Yeah, but the thing is that you need to subtract this static friction force from the applied force, and if they just equal, it will not get any acceleration. So it has to be a bit larger than the static friction force. And then this body starts to move with some acceleration, because it always has to be subtracted from the applied force. However, let's go to the next point. So we mentioned that if it's larger, then it starts to move. And then a bit different force starts to act, which is kinetic, so-called kinetic friction force. So kinetic with small k friction force is mu kinetic, also multiply n. So this is another kinetic friction force coefficient, which also depends on conditions of the surfaces of the body and the plate on which it's moving. However, always this coefficient for kinetic friction force is smaller than a coefficient for static friction force. Means that static friction force is always a bit larger than the kinetic friction force. And that is kind of correlates with some saying that it's difficult to start something, which kind of has some physical background behind it, because it's more difficult to start moving this body because of static friction force, which is larger than once you already move it, this kinetic friction force usually a bit smaller. And that's why you will this kinetic friction force will compensate applied force with a bit in a smaller extent. So this is what we need to know about, and obviously that both of these friction forces, they are directed in the opposite direction of the movement. So if we push from left to right, both the static friction force and kinetic friction forces, they are directed in the opposite direction from right to left. And once we stop moving, there is no kinetic friction force. Then if we stop applying the force, there is also no static friction force, because it appears only when we apply certain force to this body. So this also should be taken into account. If we don't apply any force, then we have only weight and reaction of the plate and nothing else. So this body just doesn't experience any other forces applied to it besides these two.
Sorry, what means mu k is less than mu static one?
It means that it's at the same n reaction of the normal reaction of the surface on which this body is located. Once we start moving, so once we experience kinetic friction force, it will be smaller than the static friction force, which was before. So it will be something like we reach, let's say maybe we can consider this as some graph over t. Let's say we increase linearly applied, so here is applied force. We increase linearly applied force until it reaches some saturation, which is this static friction force. And then once it starts moving, it just drops here. So this is already our kinetic friction force. So kinetic friction force is always smaller than static friction force for the same body and the same conditions of surfaces.
Thank you.
Mm-hmm. Yeah, there is another friction force which also should be considered. That is reaction of the environment on the on our body. So it is always equal to, so this, in this case, it depends on velocity. So if we have some, I don't know, some sphere in water, for instance, and let's say it's like flow of water around this sphere. So means that this sphere moves with certain velocity in water. So if this velocity is equal to 0, there is no, so it's called drag force. There is no drag force because there is no motion with respect of the body with respect to the environment. However, if it starts moving with certain velocity, and when this body is quite small and velocity is also low, usually this drag force, let's call it like this, will be equal to minus some coefficient k1, let's call it, v, like vector of the velocity. So what does it mean? So we have, so this coefficient is the feature of the body and of the environment. So it takes into account the shape of the body, its surface condition, also takes into account the viscosity of the liquid, so how easy it is to move through it. So if you compare, for instance, water and honey, like obviously that at certain temperature when it's still liquid, so obviously it's more difficult to move bodies in honey, which is more viscous in comparison to water. And also here is the velocity. So it linearly increases this drag force with velocity. If these bodies are larger, like comparable to some like square meters, square centimeters, I mean the cross section of these bodies, and velocities are higher, so which is very good example of some sky divers, like people who jump from airplanes. They experience quite a lot of this drag force, and in this case drag force will be equal to also minus. So this minus means it always directed opposite to the velocity vector. So this is the drag force. Minus K2, which also takes into account all these parameters which I mentioned of the body shape and environment, and then V velocity square. So this is the case when we have high velocities and drag force for this specific case. So for instance, we have some person who is jumping from the airplane with some mass m, so it experienced there is some weight mg, and then minus k2 v square equal to m a. So this will give us the acceleration with which this person will fall down. And at some point, this velocity, this product of drag coefficient and velocity square of velocity will become equal to the weight of the body. And that velocity is called termination velocity, Vt. So this is velocity which is maximum speed for falling body in atmosphere in our case. So it will be compensated, its weight will be compensated by drag force, and that means that this left side will be equal to 0. There will be no acceleration. So we can write K2V termination velocity square equal to mg. And from here we can determine the termination velocity, which is equal to mg divided by K2 square root. So this will be the maximum velocity which for a given position can be reached, let's say for a given shape of the body, and can be reached by falling in atmosphere.
Sorry,
And
why the
other
first
examples could be applied also, for instance, like some maximum speed of submarine in water when we have certain driving force of its like engines, and it will be compensated by the drag force of this friction of the body with respect to water. So these are kind of most common friction forces, and I guess next time we will have some consider some cases with these friction forces, just to see how to address problems with these forces, and move forward for some circular motion, like application of laws of motion when we have motion along circular trajectory. That is another class of questions which is relevant and would be good to discuss.
Sorry, what is the difference between the first force, like it is minus k multiplied by v, and the second force is like minus k multiplied by v squared. Why is
Yes.
the second one v squared?
Yeah, so good question. These are two, like both cases are drag forces. However, depends on the range of velocities and size of bodies. Either first equation or second will be applied. For small bodies which move with small velocity, drag force will be linearly proportional to velocity. For larger bodies with higher speeds, it will be proportional to the square of velocity. And these specific conditions always are highlighted in the problem, for instance, when you solve it. So this should be given as a parameter, like given parameters for the problem. Just wanted to highlight that drag force can depend based on different conditions in different way on velocity, but it always increases with increase of velocity. And when velocity is equal to 0, like obviously drag force is also equal to 0. Okay, I guess this is pretty much everything what we discussed today. And yeah, if you have any more questions, you're welcome to ask during our next online class on Wednesday.
Excuse me, Professor. I have one question. So in the last equation of mg minus k v squared is equal to ma. So we know that mg and drag force are opposite to each other, yes?
Yes, because this is mg, it's direction of our velocity.
But shouldn't the equation becomes like mg plus k v squared in that case? Because drag force is already minus, no?
I mean, so let's say we have this body m. So we have the weight, which is mg. Obviously, if it's falling, so let's say we have this axis going from top to down. Obviously, our velocity is directly along the axis, so it's kind of positive. And it's in the same direction as mg. So that's why our drag force will be in opposite direction because it's opposite to velocity. So it will be opposite direction to mg. That's why we write mg. It's like projection of our weight to the axis x minus k2 v squared. And then it will be equal to some acceleration again in this direction of x.
But if we plug in the value of f drag, like the total equation is like mg plus f drag is equal to ma, yeah?
Yeah, but I mean, if we put here f drag, so if we write equation in this way, mg plus f drag equal to ma, yeah, that will be right, because we don't consider now the projections. Once we consider the projections and the value of this force f drag and mg, then we have positive mg and minus k2 v squared.
Okay, thank you.
Yeah, good. So we just skip this part and put already instead of f drag, we put its expression for this force. Okay, guys. I guess our time is over for now, and hope to see you on Wednesday. Have a good evening.
Thank you. Bye.
You too. Goodbye.
Bye.
Thank you. Bye.
Thank you. Goodbye.
Thank you. Bye. Bye-bye.